Morning, everybody. How you feeling? Alright. Wow, I'm pleased to announce that my computer is being weird. So, while that's resetting, test is this week. I assume that's the big thing on most of your minds, at least as far as this class goes. Main goals for lecture today and Wednesday is test review and homework help, whatever's on your mind, whatever you're wanting help with, whatever you're wanting an explanation on, any and all of it is open to the floor. A couple of small things I want to point out about the coming days. Just a reminder of the coming schedule. Again, lecture today and Wednesday is study time. If you feel you don't need study time, or if you take the test before Wednesday, then you don't necessarily have to be here on Wednesday. Because if you don't need to study for it, then you don't have to show up necessarily. I'll leave that judgment call to you guys. What is definite is that we won't be meeting Friday the 18th or Monday the 21st. Basically, once you take the test this week, happy vacation, at least from physics. No meeting the 18th or the 21st, also no lab next week, so I will not actually see you after you see me last this week until November 28th, where we reconvene from Thanksgiving. During this week, the 28th through the 2nd, we will be giving back the test and going over it, talking a bit about sound and waves. We will also have a lab that week about waves. That'll be just the last additional concept we learn that'll be folded into the final. And the tail end of that period of time will be exam review, similar to how we do for the tests. Last day of normal class is Monday the 5th, then we have reading season, and then exam season starts on the Thursday the 8th. And that's pretty much it for the class. The test this week, much like the last one, there'll be 8 questions, 105 points, graded out of 100 points. 2 concept questions, and then 6 math questions. You'll have as long as you need, but the test was written such that it could be completed within an hour for someone at this skill level, and not that you have to. And the questions aren't designed to take time. The difficult part isn't time consumption. The point is just, can you remember and utilize these concepts? You'll have your formula sheet. If you don't have a copy, I have loads of spares. And I encourage you to ask me or Dr. Owens questions at any point during the test. Study guide is live. We can look over that together here. We can also talk about the chapter 7 and any homework stuff. Whatever's on your minds, the floor is now open. Yeah.
For number 5, I understand how you got the answer, but not when you subtract it from the Earth's radius. I didn't get that same answer.
One moment, loading. Where'd that one go? There. All right, that was the meteor, right? Yeah. All right. So, what you originally asked is, at what height above Earth's surface will this meteor begin to orbit Earth? The math that I showed over here, the process to answering this question is, gravity acts as a centripetal force, creating orbit of any object around the planet. So you take gravitational formula, set it equal to the centripetal force formula, and here I solve for radius. I do realize that my V's and my R's look kind of similar, so I just want to reiterate, this is V squared, these two are R's, these R's cancel slightly, and what I have down here, after canceling and rearranging, the V squared is here at the bottom, I divided it over, and I multiplied an R over to the top of the right. So this is a single R, this is a V squared. Solve for radius. The radius given is 13 million meters. Now this is the radius of the meteor from Earth's core. This is not the height above the ground. So to find height above the ground, I subtracted out Earth's radius. Because you have to be this far away from the core to be standing on the ground. So this then is the height above the ground. It appears to be about twice as far away from the core as you would be standing on Earth's surface.
So you take the 13 number and subtract it by 6.371.
Correct, yes. Note, this number didn't show up at all in this calculation. This number, the Earth's radius, is entirely here to convert orbital radius into height above the ground. If you'd like to see this visually, I am certainly a visual learner. Earth, meteor, weird piece of space cheese, orbital radius would be from the core, the center of Earth's gravitational effect, to the meteor itself. This is Earth's radius, and this is height above the ground. So, to all visual learners, this is why. I'll label this RE and height. This is where we live.
So the radius that was given to us in the word problem, 6.37, is that from the center of the Earth to the meteor?
This 6.371 million, that is from the center of the Earth to the surface of the Earth.
And so for this, will FG always be equal to FC?
In the case of space objects orbiting one another, gravity acts as centripetal force. Not all centripetal forces are caused by gravity, but in space, they are. In space, gravity is what acts as centripetal force to create orbit. But as the homework showed, loads of things can act as a centripetal force.
So in your diagram, what's that 13163013?
This?
Yeah.
This is the orbital radius. This is the distance from Earth's core to the meteor. That was the R that was actually found in the math. Since all the math can tell you by itself is the distance between the two objects' centers, the distances between their gravitational cores. Question?
Are we finished with this question? I just have a question on number 9.
Okay. Does everyone feel okay about this number right now?
How'd you get that 6797 number again?
All right, so this, you know what, I should write that down. This full big orbital R
Right.
minus this gave us this. $13 mil, 168 thou, blank, minus 6 mil, 371, blank, is 6 mil, 717, blank. Does that help?
Yeah.
Any objections to move on to 9? All right. here we have a torque question, not dissimilar to what we worked on in lab, although it looks it looks a little different, but the application is mostly the same as what we did in lab last week. Here we have a sine. Any specific part you want to talk about, or should I just want to go through the whole thing?
It's more B.
B?
But
All right. All right. Well, let me set up the whole thing because it's written in order for a reason. So this sign is balanced in terms of torque. This pole is attached at the wall by a hinge so that if it was released, it could swing down. I think a lot of signs do that specifically so that you can lower them, change out what's hanging on it, and maybe take them down in case of a storm. So this point here is the pivot. The end point is the pivot, and that's the point we have to generate all of our torques around. There's a total of 3 forces acting on this thing that generate torque throughout this particular question. And the goal is to balance all of them together. I'm going to rewrite it over here because the drawing on the board is already pretty busy. Pole, this is our fulcrum. The 3 forces generating torque right now are 1, the weight of the pole itself. Its weight is acting dead center, because that's how center of mass works. Then there's the weight of the sign acting on the end of the pole. And lastly, there's a single rope attached here, tied up to the wall itself, exerting force both upward and leftward on this particular signpost. So tension, Y tension, and X tension. So there's a grand total of 3 forces generating torque here. And the torques made by all of them need to cancel out, add up to 0, or else the sign doesn't stay put. Part A asks about calculating the torque that the sign and the pole themselves generate. So part A, solving for the torque made by each of those individual forces. The weights of the objects are just applied at the object's center of mass. Part B then asks, what must the tension in the rope be to hold up the sign? So part A was again just, what are these 2 torques? These are the 2 torques trying to make this system spin this way, clockwise. Both the sign and the pole are pulling in directions that would generate clockwise torque. And for angular vectors, direction is either clockwise or counterclockwise instead of forwards or backwards. So these 2 torques point clockwise. To cancel that out, tension, since it's pulling in the opposite direction, has to generate counterclockwise torque. So this is the one thing holding the sign up versus these 2 things trying to pull it down.
And so that's why the torque of the rope equals the torque of the sign and the torque of the pole.
Correct. So like with net force equaling 0 to keep something in place, net torque also has to equal 0 to keep something in place, to keep it from rotating. And that net torque is going to be made up of all of the individual torques present. We got rope, sign, and pole. So all of these together add up to 0. It's just these 2 point one way and this points the other. So this one has to be equal and opposite to the sum of these 2.
And then that's why we choose TY instead of TS.
Correct.
Okay.
Because again, about what you just pointed out, formula for torque dictates torque is only generated if the force is perpendicular to the radius. This rope isn't totally perpendicular. The tension in this rope has both an x component and a y component. The x component cannot generate torque from this angle. Only the y component can. So technically this rope is being pretty inefficient. To make it as efficient as possible, you want the rope to point straight up, but depending on the building, sometimes you can't do that, so you have to work with what you got. So here, only the y component of that tension generates torque. So the force calculated here, set the two clockwise torques against our one counterclockwise torque created by the rope. We know the radius of where the rope is applying that force, so we can solve for the force creating the torque needed to cancel out the two clockwise torques. But the force given here is again only the y component of tension, since that's the only component that makes this torque. The x component does nothing except pull the pole into the wall, which is useful, but it's not what we're looking at. So what's solved for there is specifically Ty. To get tension, the full tension, you just have to do one more trig step. Does that help?
Yes.
Okay. How does this one feel to the class as a whole? I think I saw yours first.
I have a question about the homework, so.
Oh, I was like, so how did you get the tension to come out to 1108? Because I was not getting that, I was getting 14 or something.
Okay. Do you agree with Ty being 784? All right. Well, the way that I drew this, tension is the hypotenuse. Ty would be adjacent to the 45 degrees that I'm using. So cosine of 45 should be Ty over T. Check my own work real quick. Cos of 45, although 45 degrees wouldn't really matter. Ty over T, so therefore T should be Ty over cos of 45. So 748 divided by cos 45. Oh, 784, excuse me. And that gives me 1108. I am curious where 14 would come from. I can look at your work later if you'd like.
Oh yeah, this is where is it combines in degree or radian, would that change it? Or-
Yes, because if we're given 45 degrees, it has to be in degrees mode.
Okay.
Let me,
You weren't in radian?
well, no, it has to be in degrees mode to get the right answer.
Okay.
I just put it into radians mode to check, and I got 1492. So yes, if you're given degrees, you have to make sure the calculator is in degrees mode before you press enter. I know we've been talking alternately about degrees and radians the past couple of weeks, but if it helps, for trig, I only really give angles. Trig questions, where you'll actually use sine, cosine, tangent, I will provide you angles. We will only really use radians to talk about, amount something spins, angular displacement. So you shouldn't ever need to swap your calculator's mode. Once you have it in degrees mode, it should be able to stay there. Any other questions about this one for right now? All right, you said homework, right?
Yes, for chapter 7, I'm having trouble with the first part of number 4.
Okay. So, a small reminder, B and C are now optional bonus points. They are worth no standard points on the question, so you don't have to do them. They're just challenge mode. You'll get bonus points if you do them, but they take time. So only do them if you have time and want to. Now for A, oh, my picture's offset. That's fine. Now for A, this is a centripetal force question. It's just, it looks a little weird and the angle complicates it slightly. But it is still centripetal force. There is a centripetal force causing the cue ball to orbit around this central point. So it's orbiting at a certain radius from that center, and there's a certain centripetal force causing that orbit. That force does specifically point towards the center, and what makes this a little complicated is that the force, from how I'm holding it, from how the picture is shown, definitely points to the right, but the rope that's doing this isn't in the right axis. It's tilted like this. The only rightward pointing force acting on the cue ball is the X component of the tension. So the tension here at this angle is kind of pulling double duty. The X component of tension is the centripetal force. That's the only force present that will always point towards the center of this circle, because as the rope keeps changing, that inward pointing vector keeps changing too. So the X component of tension is going to be the centripetal force here. Meanwhile, the Y component of tension, since it's always going to point up, is combating gravity. So the Y component of tension adds up with gravity to equal 0, and that's why the cue ball isn't falling or ascending. And the X component of tension, unbalanced, is serving as a centripetal force. So an amount of the complexity here is 1, reaching that conclusion, and 2, determining how you can get all the numbers you need. Because the way I'd recommend doing this is using the centripetal force formula. There's a certain centripetal force making this mass accelerate based on its velocity and its orbital radius. We were asked for speed, linear velocity, so this version of the formula instead of the one with an omega in it. We were told the ball's mass, but we need something to plug in for both R and centripetal force before we can get to V. So analyzing this picture, I've separated it into 2 separate similar triangles. Because the angle of the rope determines both the physical radius of the circle and also how the tension gets divided up. So this same angle, that original triangle, is serving double duty and affecting 2 different pieces of trig that happen to overlap in the same region of space. They overlap through the rope. Physically, in terms of just the physical string and where it is in the universe, string's hypotenuse, my sample numbers put it at 2 meters long. This X component of that vector will serve as the physical orbital radius of the circle, which I hope can be seen in the original drawing. So that is where our R is going to come from. We know that the string makes a 30-degree triangle with the vertical. We don't actually end up needing the Y component at all, but we do need the X component because that's the radius of the circle. So sine of 30 degrees equals opposite over hypotenuse. This can tell us the radius of the circle. 30-degree isosceles triangle. R is 1 meter long using these sample numbers. Now, simultaneously, same angle but different vector in the same region of space. the angle of the rope also determines the angle that the rope's tension exists at. So the rope has some tension in it. We don't technically know how much, but we know it must. We know that the y component of that tension is equal and opposite to gravity, and the x component of that tension is what we want for our centripetal force. So we somehow need to figure out this piece of the triangle. Now we know the angle, but we weren't told tension. Instead, we've surmised the y piece must be equal and opposite to the weight of the cue ball. So we may not know the hypotenuse, but we can hypothesize the y piece of this triangle. Since that y leg has to be equal and opposite to gravity, or else the cue ball isn't stable vertically. If they weren't equal and opposite, it would move up or down. So using this, you can find the weight of the ball. That would also have to be Ty. And we can find Tx with Ty in the angle, as opposed to how we normally would say the hypotenuse in the angle. This would just require us to use tangent instead of any of our other functions, because from this 30-degree angle's perspective, Tx is the opposite leg, Ty is the adjacent leg. So TOA, tangent, opposite, adjacent. Tangent 30 will be x over y. The y leg, again, should be equal and opposite to the weight. So finding the weight to be 4.9, that should be the same for everybody. 4.9 times tangent 30. The 30 is also the same for everybody. Will give you the x component of your tension, which again is our centripetal force. So this then, what we find for Tx, is what we'll plug into the formula for Fc, along with the previously calculated radius for R. That should allow you to solve for your v squared. Yes?
So the thing that I was missing was the assumption that gravity and Ty are the same. Is that an assumption that might come up on the test, or is that maybe a little harder than the test, or?
I'll go ahead and tell you it won't. The angle part of this question, the fact that it's forming a cone, is unique to this problem. It is just force analysis, but again, you're not trained in these assumptions yet. So that is the wrinkle of this homework question, and it's not reflected on the test. The centripetal force stuff is, but not this assumption. That is also partially why B and C are now optional bonus points. Does that help your concerns?
Yes, thank you.
All right. Yeah, the angle thing isn't an issue when there is no angle, when it's just a flat disk, because in that case the tension would just entirely be centripetal force. And you wouldn't need to make that assumption otherwise. Yes?
For question 6 on the study guide, part C, why is the angular acceleration 0?
So, and I'll admit, I may have left a word out of my writing that would have made it a little more obvious. Okay. For number 6, you're examining this merry-go-round. It is moving at a constant 15 full rotations per minute. Constant angular velocity means what for angular acceleration? It's 0. There is no change, therefore alpha is 0.
Where does it say consonant?
That's the word I left out. my intent was for it to be constant, and therefore this is 0. But I technically didn't actually say the word constant. On some level, I feel the assumption is there, but it's an assumption that I'm making, and I'm the one that wrote the question. So I apologize for that inconsistency.
I got 2 questions. One's on the study guide. Can you, so on number 7, you set up your equation as like J equals the change of P equals F times T equals M and the change of velocity. How did all that stuff just equal each other like that?
So impulse J is defined as change in momentum. So this is a definition. Really, you could leave one of these steps out if you wanted to.
Okay, because that's what made it confusing. It was just that there was like 4 things.
Yeah. My intent was to write out the whole of it to remind you that all of these are impulse formulas.
Okay.
But I only ended up using one of these 2 parts to define what I was doing as the left side, and then mass times change in velocity to actually calculate the impulse. I do use this part later on, so maybe my logic was write all of it down up front, and then we'll piecemeal it out over time.
Okay. What's P again? What's that verb?
That is rho for momentum. Linear momentum.
Okay, my other question is 2 on chapter 7's homework.
All right?
I got all the numbers, and I'm pretty sure I did the math right when I was using the force of gravity equation, but I didn't, I just kind of ran into problems to figure out what to subtract from what, or to add to what, since there was that third mass in the middle.
Right. So the 2 forces that you need to find for 2A are the force from object 1 on object 3, which will point this way, and the force from object 2 on object 3. And I'm numbering them in the order that they were first mentioned.
Okay.
The original prologue gives you these 2 masses spaced so far apart. And then the part A itself puts this third one in the middle.
Right.
It is asking you what are the forces from 1 and 2 respectively on 3, and figure out what then the net force on 3 is. So the 2 different objects are pulling it in 2 different directions. The larger one is going to win. So at least for my sample numbers, the second one listed is the bigger one, 300 kilograms versus 600 kilograms. So the second object is going to pull harder. That's going to be the one that wins this fight. Hence why the answer is being pulled towards the bigger one. That part of the answer is that. As for getting the number itself, you need to use universal law of gravitation formula twice. Once for using mass 1 and mass 3 to figure out the force mass 1 exerts on mass 3, and a second time using these 2 masses for the force mass 2 exerts on mass 3. So what I've got here on the board, first is force of gravity from object 1 on object 3. That's using both mass 1 and mass 3, which I will label a little better. The radius would be actually half of the first R that you're given, since it's you were told the total distance between 1 and 2, and 3 is placed dead center of the pair. So whatever your R is, cut it in half before you square it. And that will give you so much force. This will be the smaller of the 2. The other force, the force from object 2 on object 3, will use mass 2 and mass 3, replacing mass 1 with mass 2 instead. Every other number is actually the same though, because G is constant. They happen to have the same radius, and M3 is constant throughout all of it. that gives me these two forces pointing in opposite directions. And technically they need to be added together, but since they point in opposite directions, it's functionally subtraction.
Okay. Okay, so you subtract the 2.61 from the 5 to
Correct.
5.7.
Now, if you're looking at my Sable calcs and comparing them to the answer on the board, technically, the number here is the same as the number for that first force by itself, but that is a coincidence for my sample numbers. That only happened to me because my second mass was twice as big as my first one. Therefore, the force generated by the bigger mass was twice as much as the first one. This is double this. So if you subtract the smaller one from the bigger one, you get half of this one, which is the same number as this one, purely coincidentally. That would only happen to you if your M1 and M2 are similarly related. I think in previous times I've loaded this up, they weren't. One was not double the other, so I believe that is just random, pure randomization. So that is if you're analyzing that, promise it's coincidence. Did that address your concerns?
Yeah, actually, I got my math went all the way through for the final answer, and it's actually the way I typed it in. I tried to do like the times and the negative. I didn't know, I forgot left side is like the E
Yeah.
for it, the minus. So, I'm all good now.
Okay. And again, B is optional bonus points because of the sheer amount of algebra it takes to figure that one out. Which will also not be a test question because that would take you half the test time. Yes.
As far as the test questions, I know it wasn't in the study guide, is like kinetic energy conserved gonna be something we should review? Or it's not really the kind of question we went over in class.
Right. Something that you do need to remember is what type of collision conserves kinetic energy. Off the top of your heads, plural, which type of collision conserves kinetic energy?
Is it inelastic?
Elastic, very good. Elastic collisions conserve kinetic energy. So if we look at the study guide, for example, because I'm not going to show you the test itself. Number 10 gives you a sample collision and then asks you to work it both inelastically and elastically. When you work it inelastically, you cannot assume kinetic energy is conserved, therefore you have to examine it through the conservation of momentum and nothing else. Overall, inelastic ones have the potential to be a lot simpler for that reason. B is the elastic way, which has the potential to take more time. Because elastically, both momentum is conserved and kinetic energy is conserved. So you can analyze it through the lens of momentum, but also through the lens of kinetic energy conservation. And frequently, conservation questions like this, collision questions like this, in an elastic collision, it's often the case that you don't know what the final velocities are because everything tends to bounce off of each other very chaotically. Inelastically, things tend to stick together and share final velocities. Elastically, they don't. Hence the two unknowns in my momentum analysis, which required a second equation to help me do two equations, two unknowns to get to the answer here in the key. elastic collisions have 3 different starting points you can use because momentum's conserved, kinetic energy's conserved, and some very smart people combined those 2 principles into that 3rd starting point up there. So in the test, you'll be told what type of collision something is. And based on the type, you will have the information, you should be able to then determine, can you figure it out through momentum? Additionally, can you or should you examine kinetic energy to help you get your answer?
Is kinetic energy equation used for elastic flow?
It can be, yes. Kinetic energy is only conserved elastically. I could ask you if I wanted to ask you about kinetic energy in an inelastic collision, I might ask you how much energy was lost, which would be find the total KE, find the initial total KE, find the final total KE, and subtract them from each other, which I also think I showed in 8, although it's angular kinetic energy. Yes.
I think you had said, since we kind of brushed over it kind of fast, that the angular momentum would be worthless, or you?
Yes. Angular momentum and angular kinetic energy are each only mentioned once, and it's basically, can you look up and use the formula for each one? Those specific parts are worth a very small fraction of points total.
Can you, when I was doing 8, I understood all the math and stuff for part A, but can you just explain the setup for part B? Because there's
8B?
Yeah, 8 for me.
So this gear collision is technically an angular inelastic collision. As a result, you're going to lose kinetic energy. And the question was just to find how much was lost. So this piece here, it's supposed to say KE angular initial, so KE theta I. And initially, the only thing with KE was gear number 1. So formula for angular KE, make sure it's written more clearly on the board, is 1/2 times moment of inertia times angular velocity squared. So to figure out the initial energy, we would use gear 1's moment of inertia and gear 1's initial angular speed. And that would give us an initial amount of angular kinetic energy that gear 1 had before the crash. After the crash, gear 1 has slowed down and gear 2 has now started moving. So both gears have some amount of kinetic energy on the final side. So this is total KE angular final. So now both of these objects have KE. So the 2 parts of this are finding separately how much KE each gear has afterwards. That would be each specific object's moment of inertia and their shared final velocity squared. And combined, after you find each individual KE and then add them together for the total final KE, there's a very small amount left. So this is what's left. This is how much there was at the start. The difference between them is how much that was lost.
Okay, so it's just like using the same formula, but for each formula with respect to one of the gears. Okay. So
One of the gears at one moment in time.
So how come we have another KE equation? Or a KF equation? So like on that second row, we have like 1/2 I.
1/2 I1
Right.
angular velocity final,
Right.
and then 1/2 I2 angular velocity final. So this is the two different kinetic energies of the two different gears
Okay.
based on their specific moment of inertia and the angular speed that happens to be the same for both.
So it is comparing two gears.
Yes,
together.
this is two separate gears in the after state.
Okay. And then, so one line above it, how, where we just have like the raw, equation at the very first line, what are all the, how did we get like 4 numbers in those parentheses when we plugged it in? Like what's the equation straightened out?
So, okay, yeah, let me rewrite that to be a little bit bigger. Anyone, is it okay if I erase the torque flagpole? All right, so KE angular initial for this particular system So, in the initial state of this particular system, only gear 1 was moving. So initially, only gear 1 had any kinetic energy. We could add on gear 2's information, but since it wasn't moving yet, its angular speed would be 0 and its whole piece would fall out. Does that make sense?
And this is like the very first time they make contact and it's rubbing against the gear trying to get it going?
This is before they ever touch.
Oh, okay.
This is before the crash ever happens. Gear 1 is just spinning by itself.
Okay.
The final calculation is after they've completely meshed together and are now both at their final speed.
Okay.
This is initial before they've ever interacted. This is gear 1 by itself spinning at that initial speed. And how this exploded into all of those numbers is that we needed a formula for I, for moment of inertia of a solid disk. And when the words solid disk appear in a question, that tends to be your invitation to check this chart to remind yourself what the formula for moment of inertia of that shape is. In this case, a disk is just a thin cylinder, so 1/2 times mass times radius squared.
Okay.
So that 1/2 times m times r squared gets plugged in place of I. Sorry.
Okay. That makes more sense now. I also thought like this was right when they made contact and they were rubbing against each other. And
That's fair.
I was trying to figure out why we didn't have the other gear in the first part of it.
Yeah, if I were to be more academically correct and show what the second gear was doing at the same time, since it wasn't moving yet, its initial speed is 0 and the whole thing just goes away.
Right.
So I just kind of skipped that part.
That's fair. Okay. There's just a lot of equations.
Very fair.
Yeah.
And when I'm making my study guides, sometimes I underestimate how much space is needed for all of the work. So I apologize for that. Wow, that's the end of the official lecture period, so I'm not going to keep you from anything else. If you have the time and or want to stick around for more questions, you are allowed. And we also have more studying on Wednesday. And there's normal study sessions on Tuesdays and Thursday nights. Let me know what you need as you're studying or before you take the test, and have a wonderful day.